Okay, Georgina, if you want to take it away with the introduction.
Absolutely. Thank you, John. Hello, everyone, and welcome to the Geospatial Forum. I'm Georgina Sanchez, Research Associate with the Center for Geospatial Analytics. And today I have the great privilege to introduce our guest speaker, Dr. Leila Hashemi-Beni. Leila is an assistant professor of geomatics and director of the Geospatial Science and Remote Sensing Laboratory. This is in the Department of Built Environment at NCANT. Her research expands across a wide range of topics. Leila does work that includes multi-temporal and multi-source data fusion, image classification, 3D data modeling, UAV and satellite remote sensing and data analytics, automatic matching and detection change, and developing GIS and remote sensing methodologies for environmental management. Leila has contributed over 50 peer-reviewed publications and scientific reports that include a book on geomatic solutions for disaster management. Leila has led projects funded by NSF, NOAA, NCDOT, and industry. In fact, pursuing funding is how I first met her. I had the privilege to work with Leila and other great researchers from across the triangle to draft an ambitious proposal in response to the Forethought RTI Research Challenge. And as a fun fact, I learned actually just today that we share a good friend and mentor. I went to Michigan State University and work under the supervision of Dr. Puyong Najadashemi, and I learned from him today that you guys are friends as well, and that Puyong asked me to say hi, so hi from him. Today, Leila will share her insights on new ways of thinking about data-driven geospatial methods to support environmental management. Just a couple of housekeeping aspects. Please remember to keep your microphones muted. We will have time for questions at the end of our presentation. And you can either type your questions in the chat box, or you can go ahead and unmute yourselves and ask the question directly. Leila, thank you so much for joining us today, and the floor is yours.
Thank you, Georgina, for your nice introduction. Good afternoon, everyone. Thank you for having me. I'm very excited to talk about some of our research activities in the Geospatial and Remote Sensing Research Lab in A&T State University. During my presentation, if you have any questions, feel free to interrupt me at any time. Also, there will be some time for questions at the end of my presentation. So today I'm going to talk about the data-driven geospatial model, methods for environmental management. As we know, almost all environmental data that we have today can be classified as geospatial data. Geospatial data basically tell us what is happening where and when. This type of data can come from the different sources. Some come from satellite imagery, drone, LiDAR, GPS. Some come from existing maps and survey like census data or field survey. Some other data can be collected by citizens that normally we say citizen science, that this data can be collected by mobile phone applications. So in environmental study, generally, we are working with many variables or parameters that change over space and time. And each single of these variables, such as population density, soil type, land use, or terrain characteristic, tell only a part of a story. So linking all these variables together allow us to get a better understanding what is happening and where. So many geospatial data analytics have been developed to better analysis and understanding environmental feature and relationship between these environmental variables that influence in a given environmental condition. So Normally, our spatial modeling has traditionally relied on physical, empirical, and numerical methods to explain reality and environmental complexity. In a model-based or model-driven approach, basically we start with a solid idea of how a physical system or environmental phenomenon work. And then we consider some state or event that we want to detect. And based on that, we generate some hypotheses. After that, we develop our methodology. We call it sample in field or in lab, and try to confirm the correlation between what we record and what we are trying to detect. Model-driven approach are very powerful because they are basically based on the deep understanding of the physical system and benefit from the scientifically established relationship. But the problem is that these models are generally simplified and sometimes even oversimplified and can't accommodate infinite complexity of the environment. So they are not normally efficient for noisy data or unincluded variables. And if we have robust models, they are computationally very intensive, and they might not be suitable for performing real-time scenario. Model-driven approach generally are also expensive and time-consuming because they are based on the trial and error approach, starting with theory-based hypothesis formation and experiment-based testing. So finding a suitable model and refining that model until we create reasonable result, it takes some time. So the question is here, how we can go beyond traditional model-based or model-driven geospatial data analytics and advance our understanding of complex spatiotemporal events. We might want to think about data-driven method. Data-driven is a new way of thinking that uses machine learning to find relationship and correlation between variables that a model-based approach might not even recognize. So the goal of the machine learning normally is to generalize pattern in training data, and then you can correctly predict new data, even if they are not presented to the model before the model. But the problem of the data-driven is that this method is data hungry. That means data-driven approach generally need a good chunk of the data to get reliable and meaningful results. Some techniques like data augmentation or transfer learning are suitable to generalize from the limited training data and discover some spatiotemporal feature and decision criteria for this data-driven method. But still many approaches need really big training data set to create meaningful data. The reason is that machine learn from training data, an example. So to get reliable result, the example and the training data should be big enough to cover all full range of example and expected variation in environmental modeling. So among the geospatial data, remote sensing is one of the fields that benefit a lot from data-driven method for environmental management. So for this reason, I'm going to have a quick review on different type of remote sensing data first, and then we discuss their processing using data-driven method. As you know, our space is very busy. There are about 7,000 satellites in space for different applications such as communication, navigation, positioning, and some of these satellites are active, some are inactive. But about 1,000 of satellites are for Earth observation or remote sensing satellites. They move in their orbit and using their sensor, they collect images and information from the Earth, land, and water surface. These data are about the Earth physical, chemical, and biological system. And in addition to satellite, still we have many platforms that they can fly in different altitude. They can be drone or man-made airplane, and also we can collect data using the field sensor directly. And regardless of the platform, all of the data are collected by sensor. These sensors are mounted on those platforms. So sensor interact with object on the surface of the earth and detect and record radiation that is reflected and backscattered from an area or target in different electromagnetic wavelengths. For measuring the reflectance and emitted energy, either imaging or non-imaging sensor can be used. Imaging sensor built up a digital image of the field of view with some information about how input varies in over space and time. Optical image, SAR, thermal sensor creates imaging, they are imaging sensor. But for non-imaging sensor, one of example is LiDAR. Non-imaging sensor return a signal based on the intensity of the whole field of view. So altimeter, radiometer, and spectral radiometer are sensors that produce non-imaging data set. And all of these imaging and non-imaging sensors have their own particular uses. Here is some application just for imaging sensor as example. Optical sensor creates natural color images that look very familiar to human eyes. The data can be easily used for many applications such as land use and land cover study, agriculture application, feature extraction such as coastline, pipelines, roads, and borders. But the quality of this image always affected by the sun illumination and also cloud coverage. Other sensor that we normally use a lot in remote sensing imaging is radar or SAR. These sensors operate during day and night because they are active sensor, and each SAR data has different applications from sea ice monitoring to monitoring vegetated surface or ice sheet. But radar signal doesn't contain any spectral characteristic. And finally, our thermal sensor measure land surface temperature in different lightning conditions during day and night, and can be used for identifying surface material feature such as rock type, soil, moisture, and many other features. This, all of this remote sensing data collected actually detected by energy that is reflected from Earth. The data include spatial, temporal information, and geographical knowledge about those objects or features that we are studying. Quality of the remote sensing depend on spatial, spectral, and temporal resolution. Normally, a spectral resolution refers to the size of the area covered by a single pixel. A spectral resolution depends on the ability of the sensor to measure a specific wavelength of the electromagnetic spectrum. The finer the spectral resolution, the narrower wavelength range for a particular challenge or band that we see in the remote sensing data. And the temporal resolution normally is about the revisit time of sensor and refer to the time between image data collection. In addition, all of this resolution is still the quality of the remote sensing data is influenced by many other environmental factors, such as land cover type, the atmospheric condition, and the lightning condition. All of these factors can result in complex and diverse data quality problems. With this introduction, I wanted to highlight that we have a lot of platform and sensors that create huge amount of high spectral and also temporal data about our environment. on daily basis. So the main research goal of my laboratory is to develop effective algorithm method for combining and extracting the information contained in this rich multi-source data to enable novel views and create a comprehensive and detailed knowledge basis of the environmental dynamic for both rapid changing events like flood, landslide, earthquake, or for steady progression like erosion monitoring, precision agriculture that we monitor the crop growth, and so many other applications in environmental management. So again, for remote sensing data processing, we have two representative frameworks, that model-driven and data-driven method. Both approach has their own advantage and disadvantage. The model-driven method considers the imaging mechanism, which is deterministic and theoretically reasonable. However, they can't easily model the complicated nonlinear problem. Model-driven methods normally are based on statistical analysis, need handcrafted feature, and build a cost function and then optimize that. That again, it's really time consuming. But if we look at the data-driven, like deep learning method, these methods learn feature automatically, especially for nonlinear statistical feature, they are very beneficial. But the problem that they are over-dependent on the training data. At Geospatial and Remote Sensing Lab in North Carolina, A&T State University, we have worked on developing and applying different model-driven and data-driven methods for different environmental applications, including rapid and accurate inundation mapping, for also for smart and precision agriculture, for traffic and incident study, monitoring and of the landslide, for water quality in North Carolina, and also for the earthquake study. So I'm going to start with our first project that is funded by NSF, where we are working on model-driven and data-driven method for flood mapping. In this project, many graduate and undergraduate students have contributed to the study, and also we have many undergraduate participants that contributed to our research. Maybe there is no need to explain why flood mapping is important, when all of us know that flooding is one of the most important natural disasters in the United States and many other countries that create a lot of extensive damages of life and also infrastructure and environment. So severity and frequency of flooding have increased recently because of the expansion of the urbanization and deforestation, also because of some extreme weather like hurricane. As example, Hurricane Harvey in 2017 created about $125 billion in damage and 68 people died in Texas, according to the National Hurricane Center. By flood mapping, we mean that mapping the extent and depth of flood of water. And these maps are very important for emergency response, damage assessment, planning, and decision-making. So we're trying to create accurate and real-time or near real-time flood mapping so we can address the flood management in timely manner. Based on literature review, this diagram shows the model-driven method for remote sensing data processing to create 2-dimension and 3-dimension flood map. For 2-dimension, normally we're using a lot of water indices or some traditional image segmentation that classify the image pixel to flood or not flood, water or no water pixel. And for 3-dimensional flood map, normally we're using photogrammetry method like a structure from motion method. And also sometimes we using directly LiDAR data, analyzing them for the creating three-dimensional flood map. And so many also working on geomorphological flood index. Water indices approach are based on a spectral characteristic and are useful for mapping water feature, and they change over time. Many water indices have been developed. For example, normalized difference water index, or NDWI, is based on the spectral characteristic of water in absorbing or reflecting off green and near infrared bands. It separates the water from the background based on threshold value. So that's going to be user-defined threshold value. The NDWI and all of the water indices are very fast, but they are very sensitive to the land cover. So normally they are sensitive to the built-up area, and it's result in overestimating of flood. Regarding the image classification, in addition to the conventional remote sensing image classification, still several conventional machine learning algorithms such as random forest and support vector machine have been widely used for creating flood map. But these methods are highly dependent on the handcraft feature, and they can't handle a very large data set. To sort that, one of the advantages of using deep learning over conventional machine learning algorithm is that they can automatically learn feature from big data. They can extract high-level abstract feature automatically. That means no human intervention in feature engineering process. So the deeper the deep learning network is, the more abstract the extracted feature are, the better output result will be. So deep learning performance normally improve when the number of variation in the data increase. So again, it needs a lot of training data. For this NSF-funded project, in addition to model-driven method, we also investigating the performance of deep learning for automatic flood extent mapping using high-resolution image from optical UAV. And we investigate the hybrid method, that means integrating model-driven method and deep learning method for mapping flood in open area and underneath vegetation canopy. So this diagram shows the general methodology of the research for creating 3D map. This part, creating 2D flood map using image segmentation using deep learning, and based on the model-driven method, based on the topography data, we can combine and create 3D map. We developed and tested our method over 2 study areas, Lamberton during Hurricane Florence in 2018, and using the data of the Hurricane Matthew in 2016 over Princeville. The data used for this research include LiDAR data and also high-resolution UAV data. Both these data were collected by North Carolina Emergency Management, and we also used a flood gauge reading data by USGS. This data also used for algorithm development and also validation as ground truth. As you see in the table, our UAV resolution, the data resolution is so high, from 1.5 centimeter to 2.6 centimeters. So for a small coverage, we have a lot of the data. So deep learning is going to be beneficial to processing a large data set. So our research approach was based on fine-tuning and transfer learning because we didn't have big training data set. Fine-tuning is a process that takes a model that already been trained for a given task, and then we tune that model using new data set to perform a second similar task. So this approach allows us to take advantage of what pre-trained model already learned without developing whole model from scratch. We use this approach because, again, deep learning requires a large number of labeled training image, and because all of the remote sensing data are very rich, labeling remote sensing image is very time consuming, and we need also accuracy. So we trained our pre-trained fully connected network using a small training data set. Our small training data set include 150 UAV images at 4,000 by 4,000 pixel size. We manually annotate those images to flood non-water, non-water, vegetation, building, and others. And then we fine-tune the fully connected network. We use the data augmentation method to artificially generate new training data from this existing training data. And data augmentation is applied to basically when we are dealing with a small training data set, we can use different operations such as randomly cropping, translation, or rotation, and create to augment our training data. Then we use k-fold cross-validation for training and prediction. And finally, we assess the method using a confusion matrix. Here show the result of the approach. Left image is photo image of UAV data over Lamberton during Hurricane Florence. And right image is the classified image that pixels are classified into flood and non-flood and vegetation map. As you see, optical data is not a good choice for flood mapping in vegetated area. So our accuracy assessment done through calculating the confusion matrix. As you see that FCN achieved like 97.5% accuracy for detecting water in open area, and it increased to 98.7% by applying data augmentation. This table also summarizes the overall accuracy of deep learning, conventional machine learning like random forest and SVM, and also model-driven method like NDWI for flood mapping using the same data set in Princeville, Lamberton, and Bluff. I just forgot the name. And so the FCN segmentation, similar to other image classification method, doesn't have the ability to detect the flood underneath the vegetation canopy that we call flooded vegetation from the optical images. So this is because simply those flooded vegetation that underneath of the flooded vegetation are not visible on the imagery. For flood-prone area that mostly covered by vegetation, especially in North Carolina, it's very important to detect those areas to avoid the unseen flood that come from this area, protecting both human life and property. So this is for this reason, we try to develop a new model-driven method based on region growing that use only DEM, digital train model. This method is based on starting with the initial point or seed point where the water level is none. So if assume here is our seed point, so we consider the searching of 8 immediate neighbors in the raster file, and then if the pixel has the kind of elevation more than this pixel, that means normally it shouldn't be water pixel. based on the physics, right? The direction of the flow. And if the pixel has the elevation less than 6 pixels, that considered as water pixel. So we classify the UAV images based on the DEM, and here showing the result. This is our test image in Princefield, validation image that collected by USGS. And then this is the result of deep learning based flood map. As you see that it wasn't able to detect the water in vegetated area. And this is a region growing flood map that is calculated only based on the DEM. By integrating a hybrid solution, we created a new flood map that is, the result is very promising. And so far we created 2-dimensional flood map. For creating a 3D water surface, we can just simply intersect the 2D flood surface plane with the pre-flood DEM. But I'm just considering the hydroflattering concept, that it gives you the one of the very fast and straightforward 3-dimensional flood map. But because of our project that we wanted to look at the capability of UAV data for flood mapping, we created point cloud using a structure from motion. These point clouds are not classified and very noisy. So we overlaid the 2D flood map on top of it, and we could classify the point cloud for the water kind of area, like inundated area. So, and then using the hydroflattering concept, we removed the noise. So we had directly 3D surface from UAV data. And when we have 3D water surface, no matter from which method we calculate, if we subtract this 3D water surface from the pre-flood DEM, that gives the water depth at each point. So this is the way that we calculated water depth in each point. So we integrated deep learning and model-based for creating 3D model, 3D kind of inundation map. But for new project that we started really recently and funded by NOAA, we try to address the issue of optical data for flood mapping in vegetated area by fusing the radar and optical data, both from the UAV platform. That means it's very high resolution. The goal of our project is developing the innovative methodology based on deep learning for basically real-time or near real-time delineation of flood boundary and water depth measurement. So as you know, the data collection by optical sensor, that is passive sensor, are normally very easy to use, but it can penetrate dense cloud cover and also dense vegetation. So this is going to be addressed by fusing by active sensor, SAR sensor, and we are using UAV SAR from NASA right now, but we are hoping to collect new data by new sensor, SAR sensor that we're going to get shortly. And we are using also cloud data processing in Google Earth Engine. That is an effective process of big geospatial data and deal with scalable flood mapping. For another project, we also working on data-driven method for precision agriculture. We are working on different deep learning method to monitor the crop growth from planting to harvest. For that, also we're looking at separating wheat from crop and separating large and non-large crops, that all of them impact the yield, the crop yield. So we have developed a control plot in the ANT form by applying different treatment. As you see in the, like, we have 3 sections, and each one has different fertilizer or, nutrition treatment. And so that is for study the sensitivity analysis and also validation the deep learning method over this study area. We collected many UAV data using the different sensor and different flight height, and we calculated many crop growth indicator like NDVI, crop height, roughness, and now we are using deep learning method UNet and ResNet to extract a spatial temporal feature from this data. And for another environmental management project, we are through a A&T Center of Excellence on Connected Autonomous Vehicle, we are using deep learning method to process UAV to extract different parameters for accurate and efficient traffic management. Our hypothesis is that a physics-informed data-driven method is less costly, provide better accuracy, and enhance data. We are at very early stage for this project, and we are excited to see how going to be the result of the deep learning for calculating the traffic monitoring. We have also started to develop data-driven methods for spatial temporal analysis of 3 other applications. A study for kind of formation and monitoring of forward landslide and its relationship with many spatial temporal environmental factors that this project is funded by DOT. Also, we studied the monitoring and prediction of earthquake using remote sensing data. This project is supported by North Carolina Collaboratory. And we just started working with Wake Forest University and Central University to develop a low-cost system to monitor water quality over time using remote sensing data. This project is supported by EEG program of the North Carolina Attorney General. So for all of this project, basically, we're trying to develop and calibrate models that relate remote sensing reflectance or remote sensing information to environmental parameter using the deep learning and model-driven methods. In our project, we noticed that data-driven methods have very promising results for many different environmental applications, but also we found that data itself can't be an alternative for physical modeling. We need always include domain knowledge and consider the hybrid solution. Actually, integrating of physical base and data-driven should look at an optimal solution, and to that hopefully improve modeling, prediction, and optimization. When we combine data with informed and detailed knowledge of physical problem, and different constraints that we have in environmental modeling, it might be more reliable and meaningful. So to summarize my talk, I want to just highlight that data-driven is an efficient method for accurate, fast, automatic approach for environmental model, and that can be very beneficial for flood mapping, crop growth monitoring, landslide prediction, and also fine-tuning or transfer learning is an important approach that can overcome data limitation in remote sensing application, actually training data set. In environmental modeling, normally time and spatial dependency is very important factor, and also the uncertainty associated with them. So a hybrid approach considering both data-driven modeling and model-based approach consider fundamental analytical relationship of time and space and seems more reliable approach for environmental modeling. And regardless of the what type of modeling we are doing, always performance of modeling should be compared and validated in several study areas. But this becomes very serious in the data-driven method when we basically rely only on data for modeling, not kind of the physical aspect of the environment. So I want to acknowledge the contribution of many colleagues from different organizations and university to our research activities, including North Carolina Emergency Management, SECORA, colleague from the Wake Forest Central University, Geology Survey, and NOAA. And thanks so much for your time. If you have any question, comment, suggestion, please let me know.
Thank you, Leila, for your great presentation. Before we allow folks a little bit of time to either unmute themselves to ask a question or write questions in the chat box, I can start with a question myself. You share with us several interesting examples of environmental management applications. I am wondering, what are your insights about upscaling and how these efforts can be applied across regional scales, particularly when we think about flooding?
Yes, it's a very good question. Actually, when we're talking about upscaling, we need to look at the spatial resolution of the data. And always I'm thinking about using satellite imagery as the regional, scale. And if we detect something, especially using data-driven method, we suspect of the certain area that, we need to have more detailed observation, that can be used by UAV or drone. I consider drone as an on-demand platform. So especially at large scale, at fine scale. So for me, incorporating the satellite imagery and UAV is very, interesting combination to kind of monitor the area at large scale, as at regional or even sometimes at national scale. And when there's some, we identify some problem, we can go using the fine resolution data like UAV data or even, field survey, we provide more detailed information. But I think that data-driven is best for that because it can easily deal with the large data set, big data, that traditional model-driven remote sensing method, they are not able to do that.
And is that part of your current efforts, thinking about upscaling and how to better validate across large areas?
Yes, actually, for the NCDOT project for earthquake, for landsliding, we are thinking about that too, using the remote sensing satellite Sentinel 1 and 2 for kind of observing global, monitoring the area. And then if we suspect about any changes, then we can collect UAV data. So right now actually this is a very new project we are going to start. We're going to start with developing the model, and then we're going to look at the multi-resolution at very fine resolution to medium resolution for satellite imagery. And we try to create a model and calibrate that for, like whenever, what type of data we have, this model can create some insight, just about what's happening in that area, especially some environmental phenomena like earthquake or landslide. They are not really local events, right? They related to the rainfall, climate change. So that, I think, always we need to have very large kind of some study at larger scale, and then we can look at the local factor that also contribute to that kind of environmental phenomenon.
Thank you.
Did I answer your question?
Yes, thoroughly. Thank you. Do we have questions? Feel free to unmute yourself. Okay, we have a question in the chat. And this question is from John. Addressing your point about real-world applications for deep learning, have you tried using models that rely on recurrent neural networks that are known as long short-term models? These models are supposed to be able to incorporate physical constraints, in part by developing memory in the hidden layer neurons.
Yes, thanks, John. This is very good point. Actually, we started on that one, and also we try to use GAN network that we can transfer the optical data to kind of SAR and inverse, like vice versa. That the reason we are looking at different data-driven method because of the need. We developed a test bed for the gauge sensor in University Farm. We have a kind of gauge station there, and a camera send the continuous image of the state of the water level over there. So we are using a recurrent CNN to read the gauge information. My understanding that normally the human operator read those images to see that if water level is like, what is the kind of status of water level. But this recurrent CNN help us to, and using IoT, so we can continuously read the gauge kind of numbers. And if there is above a certain threshold, it gives alert that there is a possibility of flood. So definitely this method is very interesting, and we are going to incorporate to our research as well.
Thank you, Sasjan.
Thank you.
Any other questions from the audience? Well, if we don't have more questions, I don't want to wrap up without answering everyone's questions. But if we are reaching that point, John, do we have any announcements or follow-ups, perhaps from the GGSO?
Only that there is not a post-forum social today. That would be the only announcement.
Wonderful. So then I believe we can wrap up at this point. Leila, thank you so much for your presentation, and thank you everyone for joining us today. And we'll see you in the next forum. Thank you so much, everyone.
Thanks so much for having me and for your time.
Thank you, Leila.
Thank you. Bye-bye.
Thank you. Bye.